Okay, so last prime less than 400, I'm checking 397, and the question really is how far do I have to go to check if 397 is prime? So I checked to see if 2 went into it, 2 didn't. I checked 3, it didn't, 5 didn't, 7 didn't, 11 didn't, 13 didn't, 17 didn't, 19 didn't. It turns out you only need to check dividing primes because all numbers are made up of primes. Notice I drew a line here at 19 and I didn't check 23. The reason is 19 squared is 361. 23 squared is greater than 400. So it turns out 23 is a little farther than I need to go, but I have to definitely go up to 19. And if we relate that back to the page we were looking at up to 100, 7 squared was 49. The next prime is 11. 11 squared was 121. So we don't need 11 until we're at 121 or higher for a number. So the square root of the number I'm at tells me how far I have to look. So one way I would approach this was to say, okay, somebody asked me, is 397 prime? I would try to figure out how far to go by just taking the square root of 397. So I would just ask my calculator, hey, what's the square root of 397? And then I would look at that number and find the closest prime below it. And so 19 is the closest prime below that square root, so I have to go up to 19 to check. Right? So it turns out this is a very hard problem determining if a number is prime or not, because our main technique for doing it is to test a whole bunch of primes less than that number. And it turns out you only have to test primes up to the square root of the number. And that's kind of the important result I wanted to get at here in this activity. So new page, wrong button. There we go. So testing for primes is what we're talking about here. And to test if a number is prime or not, you basically have to check divisibility. For each prime less than the square root of the number we're at. For each prime and that's the standard test for primes. So if we picked a big number like 1,386,111, and we weren't sure if that was prime or not, we would have to start testing primes up to its square root, which is going to be significantly smaller than 1 million something, but it's still going to be quite a bit of work. Computers make that faster, but if you give a computer a big enough number, it's going to really struggle with all those divisions. Division is a complicated thing to do, right? Okay, so I think that kicks that activity in the pants. I did have a couple of other things I wanted to point out there. And I lost my other notes page. Open, save. This computer is being difficult. Okay, and then I want that one. So back to our, there we go, the sieve here. So there's some other interesting things going on here. Like notice that in the beginning, the primes are kind of close to each other. 2, 3, 5, 7, 11, 13, 17, 19, they're not too far apart. But then later on at the end, there's bigger gaps, like from 83 to 89 and 89 to 97, there's much wider gaps there. And that's interesting, like the distribution of prime numbers as you look further and further out on the number line, primes tend to get farther apart the farther you move out. But notice there are several primes close together. So what's the closest together a pair of primes can be? Oops. Anybody? What's the closest together two primes can be? see, there's nothing in the chat. Can anyone hear me?
Just one number away?
Yeah, one number away. So the closest two primes would be 2 and 3 are 1 apart. But that never happens again because there's no other even primes. All the other primes are odd besides 2. Okay, so what's the next closest two primes could be? Let's see, Renee, did you hear something? I say something, I didn't hear it.
2.
2, yeah, the next closest they could be is 2 apart. So examples of that, so 2 apart.
It would be 2 and 5.
Yeah, 3 and 5 are 2 apart. 5 and 7 are 2 apart. 11 and 13 are 2 apart. And there's a bunch of other examples moving down through that. When primes are 2 apart, these primes are called twin primes. And this is kind of cool and weird. 2 and 3 are 1 apart, and that will never happen again for primes because there's no other even primes besides 2. However, there are infinitely many twin primes out there in the universe of numbers. This goes on forever and ever and ever. So even though the average distance between primes grows the farther out we look, you're always going to find a pair of twin primes out there. So if somebody says, I found the biggest pair of twin primes, I guarantee you next year somebody else will find a pair that's bigger. Okay? It's going to be hard to find them the bigger they get, but they exist forever. And that's been proven mathematically, which is kind of, I think, awesome and beautiful. So, cool number fact. So if anybody out there happens to be 23, or not 23, 29, you're at the beginning of a twin prime with 31, kind of a cool age, 41 to 43, 59 to 61, 71 to 73, and I can't remember where the next pair is, but twin primes are kind of cool. All right, and I think my notes just got out of order, and I'll start a new notebook. There we go. And let's restart the recording. Oops, I got a chat there. And again, I have trouble seeing 3 and 5. Okay, thank you for offering that, Jimmy. And sorry, I'm having trouble viewing the chats today. I hope to figure out how to fix that soon. Okay, I'm having more technical difficulties here. There we go.